In this lesson, we're going to introduce the last topic in this lecture on network reductions or network theorems. And this relates to what is called the maximum power transfer theorem, and it relates nicely with the Thevenin and Norton theorems, and I will try to point that out through an example here. So simply put, the maximum power transfer theorem makes a claim about how you can deliver the maximum amount of power to a load from a Thevenin equivalent circuit. So here's a Thevenin equivalent circuit, and you recall, if you have seen the or you know about the Thevenin theorem, or you've watched the lecture on that, or the lesson on that, you know that any linear network being driven by independent voltage and current sources, being a one-port network, can be equivalently represented at that one-port terminal with a single voltage source in series with a resistor, or a Norton equivalent would be a current source, independent current source, in parallel with a Norton resistance, which is equal to Thevenin resistance. So now the question is the following question: what is the maximum deliverable power power to RL? Okay, that's given a VTH and RTH. So in other words, you can't change VTH or RTH; those are given. Given that, what value of RL should you choose? I guess the first question is, what is the maximum power that you can extract from that Thevenin source and deliver to the load, and what is the value of the load at which that will happen? Okay, and the answer is, well, first let's explore this a little bit, where we'll say, okay, this is, I'll call this voltage V, say current I, and the power to the load is just going to be V squared over RL, or RL times I squared, right? And we would say that I is going to be equal to VTH. This is a single loop, right? So it's going to be the voltage driving current through that loop divided by the total resistance in that loop, which is just the sum of those two resistors. So we see that the power delivered to the load is RL times that current expression. So in other words, RL times that current expression squared, VTH squared over RTH plus RL quantity squared. Okay, and we can observe a couple things at first here before we really dig into what is the maximum power. We want to consider the case where RL is equal to 0 and when RL is equal to infinity. So without even looking at this expression, if you just go back to the circuit and you say, okay, what if RL is equal to infinity? What is the power delivered to it? Well, if RL is infinity, then its conductivity is 0, which means I is going to be 0. There'll be no current flowing through that resistor, and if there's no current flowing from the Thevenin source, then there's no power delivered. So at RL equal to infinity, the load power is going to be 0. No power is delivered to the load. If the load resistance is 0, then you can have current now, but you would have no voltage. So here, let me write that V is going to be equal to 0. In the other case, I is going to be equal to 0. And we can say that we could add another expression for PL here. The power to the load is also equal to I times V, right? So if either one of those is 0, then there's no power. And that's what's going to happen at an RL equal to 0. So we see here at both asymptotes, a short circuit and an open circuit, there's no power delivered. So we're going to anticipate that somewhere in between those two asymptotic values, there is a value of RL where the power is maximum. Okay, and it turns out okay, that the max power theorem states that maximum power is delivered to the load to RL when RL is equal to the Thevenin equivalent resistance. Okay, so let's just go ahead and consider that value. If RL was equal to R Thevenin, then what would we have? We would have we're going to plug in R Thevenin for the two loads here. Right, so we're going to have R Thevenin. Let me just do it over on the side. R Thevenin over R Thevenin plus R Thevenin, so 2 R Thevenin quantity squared, VTH squared. So that's going to be 1 over 4 R Thevenin, okay, and VTH squared on the top. So VTH squared over 4 R Thevenin. That's going to be the maximum power. And I have some accompanying notes. Hopefully I will remember to link to those. But if I pull those up here for a moment, because I don't want to take the time to derive this, but it's simple to derive with just a little calculus. What you see here, let's see. Now, this is the same as what I just showed. Okay, so we can see that the if we write an expression for the load here, power to the load RL is V. I'm using VL and IL here, but V times I, and the voltage to the load is the Thevenin open circuit voltage minus the Thevenin resistance times the current that's flowing through it, right? And that whole quantity times IL. And then what you want to do is just take the derivative of that power to the load with respect to the current, and you're looking to see when that's going to be equal to 0. Because when that's equal to 0, you're at a maximum or minimum. And we know that because of the two asymptotic values of open circuit and short circuit having a power of 0, and we also know that the power to the resistor can only be positive, this derivative being set equal to 0 is going to actually be the point at which the power is maximum. So you just solve for that current IL, and we find that the maximum current, or the current at which maximum power is transferred, is 1/2 of V Thevenin over R Thevenin. Okay, and if you solve for R Thevenin, then you find that it's equal to, if you solve for R load at that condition, that operating point, you find that it's equal to R Thevenin. And here is the expression. The maximum power to the load is V Thevenin squared over 4 R Thevenin, and a rough plot of this would look like this, where the power to the load is 0 when RL is 0, and then asymptotically the power will be 0 when RL goes to infinity. Okay, let me switch back over here, and let's consider what happens right at the maximum power point here. So if we have R Thevenin and we have a load that's equal to R Thevenin, what we really have is we have 1/2 of the Thevenin voltage across R Thevenin and the other half across the load, right? And so it's a voltage divider. That's halfway, where the load voltage across the load is halfway between 0 and the open circuit voltage. Note that at this maximum power point, maximum power is not only delivered to the load, but you have the same amount of power delivered to R Thevenin, right? Because it has the same voltage across that resistance, 1/2 V threshold. Now that doesn't end up being the maximum power point for the R Thevenin. R Thevenin sees its maximum power dissipation when RL is actually equal to 0, right? Because under that condition, you would have V Thevenin that would be completely applied across R Thevenin, and that would mean that you'd have a power in R Thevenin equal to V Thevenin squared over R Thevenin. Okay. So the thing to remember, or one thing to remember, is when we talk about maximum power transfer, we can't forget that this is in the context of a fundamentally lossy proposition. So this makes sense when there is a source that has a source resistance. So in other words, if you have, say, a battery that has a Thevenin resistance that is 1 ohm, then the most power you will ever get from that load, or from that source, that battery, will be when your load is 1 ohm. If you decrease the resistance or increase the resistance either side of 1 ohm, you will find that the power decreases. So let's just do a numerical example here. Let's say that you have a battery that is 12 volts, and you have an internal resistance of 0.1 ohms. Okay, what is the maximum power that it can deliver? Okay, so we have 12 volts, we have 0.1 ohms, and the question is, if I connect some load here, what is the maximum power that can be delivered to that load? Well, it will be it'll be found when RL is equal to, our load is equal to 0.1 ohms, R Thevenin, right? And we could either use the formula above, this this formula right here. This is, let me rewrite it actually. I'll cram it in here. P, all right, here, P PL max is going to be equal to V Thevenin squared divided by 4 R Thevenin. Okay, could just use that formula. I could also, if I just simply remember that the maximum power is transferred when the load is equal to the Thevenin resistance, then we can just calculate it. Okay, so I could say I is equal to 12 volts divided by 0.1 plus 0.1, and that is going to be 60 amps, right? And then P to the load is going to be equal to V times I, right? And V is going to be, well, it's just the voltage division of 12 volts, and because the two resistors are equal valued, V is just going to be 1/2 of the 12 volts, or 6 volts. So we'd say, therefore, this will be 6 volts times 60 amps, or 360 watts. So if you have a 12 volt battery that has an internal resistance of 0.1 ohms, you can never extract more than 360 watts from it. Either way, if you increase their load resistance or decrease the load resistance, you will never be able to get more than 360 watts out of it. And by the way, while you're extracting 360 watts from it, you will also be dissipating 360 watts inside of it in its Thevenin resistance. The battery source itself, the voltage source inside that battery, will actually be delivering 720 watts. So you'll have 720 watts coming from the battery. You'll have 360 watts going to the internal Thevenin resistance, and you will have, well, we don't know if, yeah, well, assuming that that load is actually some resistor, then we'd be generating another 360 watts of heat. Or if it's something other than a resistor, it's doing work, it's ultimately going to heat eventually. So let me look at one other example now to show you how this maximum power works with along with Thevenin, a Thevenin theorem. Actually, before I go on to that, let me point one other thing out. Okay, if you were asked for this problem here, we have a battery, a Thevenin resistance, and a load. If you're asked, how could you maximize the power to the load? And it was asked in a very general form, and it didn't tell you that you could only turn the load resistance, okay? It didn't restrict you just to that. Then the best thing that you can do to increase the power that's deliverable to a load is not to pick the resistance, the load resistance, to a particular value, but first it would be to set the Thevenin voltage resistance to actually be 0, right? So the best option for maximizing power to a load, RL, is first to set our Thevenin to 0, right? Because then P to RL is going to be simply V Thevenin squared over RL. Okay, however, one usually does not have the option to change our Thevenin. In other words, usually that's part of the stated problem, right? So just keep that in mind, because if you are not being constrained to not change our Thevenin, then the way you want to maximize power to the load is to not make the load resistance equal to Thevenin resistance, but make the Thevenin resistance go to 0. And because then all of the power that the voltage source is delivering actually goes to the load. None of it gets dissipated in our Thevenin, and there's then actually no limit to how much power you could deliver to the load. Okay, let's look at the example. In closing here, we'll look at the example from when we introduced Thevenin's theorem. We had this circuit here, and we said, what's the Thevenin equivalent to this? Now I want to augment this a little bit by saying we have this resistor, R3, and we would say, the question might be, find R3 that maximizes power, the power delivered to it. Okay, and then what is that maximum power? So initially it might seem a little bit intimidating to think that you're going to have to write an expression for the power in R3 in terms of these other, what's going to be in total in terms of 5 elements, and then you're going to have to look at how power changes as a function of R3 and find the maximum. And that's what you'd have to do if you didn't know about Thevenin or maximum power theorem. Because we know about those, we can go about this very simply. All we have to do is, if we look at the rest of the network that connects to R3, and we say, let's replace all of that network with a Thevenin equivalent circuit. And if we find what that Thevenin resistance is, then that is the resistance of R3 that will maximize the power delivered to R3. And if we find V Thevenin, then we can easily find the power that's delivered, the maximum power that's delivered to our load. So in the previous lesson we derived the Thevenin equivalent. I'll do it again here quickly. We'll find so Thevenin equivalent circuit, that's what we're going to do first. We're going to find that our Thevenin is just simply going to be equal to, if I turn off my sources, remember, turn off the sources, so I'll have R2 and R1 are in series, this is V1 equal to 0, remember short, and this here is I2 equal to 0. So I've turned both the sources off. So our Thevenin is just R1 plus R2, which in this case is 5 ohms. Okay, and then the second one I want to find is we'll find V open circuit, V Thevenin. Remember in that case there'll be no current flowing out through here. So therefore we're looking just at I2 flowing around here, producing a voltage drop here. So we can say V Thevenin, or V open circuit, is going to be V1 plus R1 times I2. And when you plug in numbers, that will be 2 plus 2 ohms times 1 amp, or 4 volts. So this will be, so then we can write 4 volts, 5 ohms, and now we can say R3 is going to be equal to 5 ohms, and the maximum power, PL max, will be equal to V Thevenin squared over 4 R Thevenin. So that's 16 volts squared over 4 times 5 ohms. So 4/5 of a watt. And so that is our answer. 5 ohms. 5 ohms for our load, and 4/5 of a watt is the maximum power that we can extract from that circuit. So I think I'll close there, and I'll see you next time.